Hello everyone, my name is Krushi. Today we will discuss about the chapter Physical Properties and Molecular Structure. Introduction. The various methods used for the study of molecular structure may be broadly classified into the following two types. Method based upon the study of physical properties of substances such as molar fraction, optical activity, magnetic susceptibility, paracore dipole moment. Spectroscopic methods such as rotational and vibrational spectroscopy, electronic spectroscopy, Raman spectroscopy, nuclear magnetic spectroscopy. The study of molecular structure on the basis of physical properties is based upon the fact that the physical properties listed above are additive as well as constitutive. An additive property of a molecule is defined as the property of the total value of which is the sum of the values of its constituent atoms. A constitutive property of a molecule is defined as the property which depends upon the constitution of the molecule, that is, arrangement of atoms within the molecule and the presence of multiple bonds, rings, etc. in the molecule. Spectroscopic method have already been discussed in chapter 3. Now in this chapter we will take up a brief discussion of important physical properties, namely optical activity, dipole moment, and magnetic susceptibility one by one. Firstly, we will discuss about optical activity. First one is plane polarized light. If a ray of light travels in any direction, it has vibrations in all directions at right angle to the path of propagation. If this light is passed through Nicol prism, then the light which emerges out of prism is found to have vibration only in one plane. This light is called plane polarized light. Nicol prism, thus used is called a polarizer. Optical activity. If the plane polarized light is passed through a plane of quartz or turpentine oil of solution of sugar taken in a glass tube, it is found that in the light that comes out, the plane of the polarized light gets rotated. The substance like quartz, sugar, etc., which rotate the plane of the polarized light are called optically active substance, and the property of a substance to rotate the plane of the polarized light is called optical activity. The substances which rotate the plane of polarized light to the right are called dextrorotatory, and those which rotate the plane of polarized light to the left are called levorotatory. This method of observing the rotation of plane of the polarized light is based upon the following principle. If the plane polarized light is passed through another Nicol prism which has its axis parallel to that of first Nicol prism, the light passes through the brightness is observed through the eyepiece. On the other hand, if the second Nicol prism is placed with its axis at right angle to that of the first prism, the light is completely cut off and field of view in the eyepiece is dark. At all other positions, the brightness is less, but there may not be complete darkness. It is observed that if the two Nicol prisms are set at the crossed position so that the field of view is completely dark, and then the optically active substance is placed between the two prisms, the field of view becomes somewhat bright. The second prism has to be rotated through certain angle about the line of propagation of light to get complete darkness again. This clearly shows that after passing through the optically active substance, the plane of the polarized light has been rotated. The degree of rotation depends upon the rotation required to be given to the second Nicol prism to get the darkness again. Thus, just as the first prism polarizes the light and is called polarizer, the second prism analyzes the light and is called analyzer. Specific rotation. The angle through which the plane of the polarized light is rotated or on passing through the solution of an optically active substance depend upon the following factors: nature of optically active substance, concentration of solution, length of solution, that is the length of the tube through which the light passes, wavelength of light used, temperature of solution. Thus, if m grams of substance are dissolved in v mu ml of solution, so that the concentration of the solution is m by v gram per milliliter. L is the length of the tube in decimeters and alpha is the angle of rotation in degree. Then it is found that alpha is directly proportional to concentration in gram per milliliter multiply length of the cube in decimeter. Hence, specific rotation of a substance may be defined as the angle of rotation produced when 1 gram of substance is dissolved in 1 ml of solution. Concentration of solution is 1 gram per ml and the length of solution through which light passes is 1 decimeter. In all reported values, the concentration of solution is taken in grams per 100 ml of the solution. Thus, if C gram are dissolved in 100 ml of solution, then we may put M is equal to C and V is equal to 100. This gives from equation 2. Further, if instead of solution substance taken in pure liquid or solid, then M by V is replaced by density D of pure substance. This gives from equation 2 alpha power of T is equal to alpha by L into D for pure liquid or solids. Molar rotation. The molar rotation is obtained by multiplying the specific rotation with the molecular weight of substance and dividing the result by 100 to reduce the magnitude of number. It is usually represented as m gamma power T. Thus, m gamma power T m alpha gamma power T upon 100. Measurement of optical activity, that is the angle of rotation alpha. The instrument used for the measurement of amount of rotation caused by an optically active substance to the plane of polarized light is called polarimeter. The principle of the instrument has already been discussed. It consists essentially of two nickel prism are called polarizer and the other called the analyzer. Both of these are fitted on the opposite end of the same metal tube. However, the polarizer is fixed but the analyzer can rotate it about the axis of tube. In between the polarizer and analyzer, there is a space for keeping the glass tube containing the solution. The glass tube is usually 5 cm, 10 cm, 20 cm, 25 cm and has glass windows on both ends. A circular scale is fixed on the metal tube near the analyzer. In the procedure, first of all, monochromatic light from a suitable source, usually sodium vapor lamp, is passed through the instrument without placing the tube containing the liquid or the solution. The light emerging out of the analyzer is viewed through the eyepiece. The analyzer is then rotated slowly till the field of view is completely dark. This gives the initial reading of instrument. Now the tube containing the liquid or the solution of known concentration is placed and the shutter closed. On seeing through the eyepiece, the field of view is no longer found to be dark. The analyzer is rotated slowly till the field of view is completely dark again. This gives the final reading. The difference between the final reading and the initial reading gives the angle of rotation alpha. If it comes out to be positive, the substance is dextro-rotatory, and if negative, it is levo-rotatory. Modern instruments have numerous improvements over the simple type. However, the basic principle remains the same. Optical activity and constitution. Optical activity is a purely constitutive property, that is, it depends upon the arrangement of atom within the molecule. It has been observed that the organic compounds which are found to be optically active contain at least one carbon atom to which four different atom or group are attached. Such a carbon atom is called an asymmetric carbon atom and is usually shown by putting a sign of star over it. A very simple example of a compound is that of lactic acid. It is found that such a compound exists in two forms, one of which rotates the plane of the polarized light to the right and is called dextro-rotatory D form or plus form, and the other which rotates the plane of polarized light to the left and is called levo-rotatory L form or minus form. The two forms have the same constitution, that is, in each form the asymmetric carbon atom is attached to the same four atoms of group but differ in their configuration, that is, arrangement of atoms or groups in space. Thus, the two forms are space isomers called optical isomers. Lebel and Bontoff pointed out the differences in the two forms by suggesting that in case of such molecule, the asymmetric carbon atom is present in the center of a regular tetrahedron and the four atoms or groups attached to it are present at the corner of tetrahedron. This gives rise to two different spatial arrangements which were like the mirror image of each other. As you can see this in the figure, the above two configurations are different in the sense that they are not superimposable over each other. Thus, the two forms are related to each other as the right hand is to the left hand of same person. The above two forms may be represented in a simplified way. In form 1, The arrangement from H to OH is clockwise, and in form second, the arrangement from H to OH is anticlockwise. Hence, if one of them is dextrorotatory and the other is levorotatory, however, by mere inspections of the configuration, it is not possible to predict as to which form is dextro or levo. The two forms are said to be enantioopposite morph form. Further, if equimolar quantities of the two forms are mixed together, a third form is obtained which is optically inactive. This is obviously due to the fact that the rotation caused by one form to the right is nullified or compensated by the equal rotation caused by the second form to the left. This process is called external compensation, and the substance thus obtained are called racemic mixture or DL form or plus minus form. This form can be separated into D and L form by suitable method. In case of compound containing two asymmetric carbon atoms, example tartaric acid, a fourth form is also found to exist in this form by the rotation caused by half of the molecule is compensated by the other half within the molecule for tartaric acid. This form, which is optically inactive due to internal compensation, is called mesoform. Lastly, it may be mentioned that optical activity is found not only in the organic compound containing an asymmetric carbon atom but also in compounds which contain other asymmetric atoms like nitrogen, sulfur, silicon, cobalt, tin, etc. Further, some compounds may not contain an asymmetric atom but are optically active because the molecule as a whole is asymmetric, that is, no plane can divide the molecule into two identical halves. Thus, it may be concluded that the optical activity is a property related with asymmetry of the carbon. Hence, optical activity can be used to test the presence of asymmetry in the molecules. When compounds like lactic acid are synthesized in laboratory, there is equal possibility of formation of D and L form. Thus, the equal amounts of D and L forms get mixed up and a racemic mixture is usually obtained. The optical activity of quartz is due to regular arrangement of molecules within the crystal spiral arrangement. Dipole moment. General introduction. Polar and non-polar covalent bond. A covalent bond is formed by the mutual sharing of electrons between two atoms. If the two atoms are identical in H2, Cl2, etc., the shared pair of electron is attracted equally by both the atoms and hence it remains exactly in the center of two atoms. Thus, neither of the two atoms in such molecule acquires positive or negative charge. The bond thus formed between two identical atoms is called non-polar covalent bond. On the other hand, if the two atoms are dissimilar, example in the HCl molecule, chlorine atom is more electronegative than the hydrogen atom, hence the electron pair is more attracted towards the chlorine atom than towards the hydrogen atom. In other words, the shared pair of electron is more displaced towards the chlorine atom than towards hydrogen atom. As a result, the chlorine end of molecule acquires a slight negative charge while the hydrogen end of molecule acquires a slight positive charge. The bond thus formed between the two dissimilar atoms have slightly different electronegativities is called a polar covalent bond, and the molecule is called a dipole because it has developed positive and negative poles. Thus, the situation is hydrochloric acid may be represented as shown in figure 5.6. Dipole moment of a diatomic molecule. The extent of polarity or polarization of molecule is expressed in terms of dipole moment, which is defined as follows. The dipole moment of a polar diatomic molecule is the product of the charge on each end of the molecule and the average, the distance between the center of their nuclei, that is the bond length. In general, for a polar diatomic molecule AB in which atom B is more electronegative than A, if plus q is the charge on the end A and minus q on the end B of molecule, and D is the average distance between the center of their nuclei, then the dipole moment of molecule AB is given mu is equal to q into D. Obviously, if the molecule is non-polar, q is equal to 0 and hence mu is equal to 0. Units of dipole moment. The charge present on the ends of molecule is usually of the order of 10 raised to power minus 10 ESU, and the distance between the atoms, that is bond length, is usually of order 10 raised to power minus 8 centimeter. Therefore, mu must be of the order of 10 raised to power minus 10 and 10 raised to power minus 8 is equal to 10 raised to power minus 18 ESU centimeter. This value is called 1 dBi after the name of pioneer worker in this field. Thus, 1 dBi is equal to 10 raised to power minus 18 ESU centimeter. Vector nature of dipole moment. The dipole moment is a vector quantity. It has both magnitude as well as direction. It is therefore represented by an arrow pointing from positive end to the negative end of the molecule. Dipole moment of a polyatomic molecule. In an polyatomic molecule containing more than two atoms, every two bonded atoms have their dipole moment. This is called the bond moment. The net dipole moment of polyatomic molecule is the resultant of different bond moments. Obviously, the resultant will depend upon the direction of the bonds. Thus, if a molecule AB2 contains two AB bonds at the angle of theta and mu AB is the value of each bond moment, then the dipole moment of molecule will be mu is equal to 2 mu AB cos theta upon 2. As mu is known for experiments, therefore knowing the value of theta, the method is usually used for the calculation of bond moments. Alternately, knowing the value of mu and mu AB, the method can be used for calculation of theta and hence for predicting the shapes of molecules. The experimentally observed values of dipole moment of some common molecules and the calculated value of bond moments of some common bonds are given below in table 5.1 and 5.2. H2Cl2 Br2 I2 N2 म्यू की वैल्यू इनके लिए होती है 0, CO2 CS2 SnCl4 SnI4 के लिए होती है म्यू की वैल्यू 0, HCl की होती है 1.03, HBr की 0.78, HI की 0.38, H2O की 1.84, NH3 की 1.46, H2S की 1.10, SO2 की 1.63, N2O 0.17, CO 0.12, PH3 0.55, PCl3 0.78, HCN 2.93, aliphatic CH4 C2H6 C2H4 C2H2 0, CCl4 CBr4 0, CH3Cl 1.86, CH3Br 1.80, CH2H5OH 1.85, CH3COH 1.74, aromatic chlorobenzene 1.73, bromobenzene 1.71, iodobenzene 1.20, nitrobenzene 4.23, aniline 1.56, phenol 1.70, para-dichlorobenzene 0, meta-dichlorobenzene 1.72, ortho-dichlorobenzene 2.50. For a more general molecule ABC with two bonds AB and AC having bond moments mu1 and mu2 are and inclined at angle theta, the dipole moment of molecule by parallelogram law will be mu is equal to mu1 का square plus mu2 square plus 2 mu1 mu2 cos theta square complete का square. It may be calculated graphically. The resultant dipole moment of groups like NO2, NH2, CH3 have also reported. There are called group moments. Their values depend upon whether the group is attached to an alkyl radical or an aryl radical. The values of few groups are given below. Group moment in alkyl NO2 minus 3.05, in aryl group 3.93, CN की वैल्यू एल्काइल ग्रुप में -3.46, एराइल में -3.99, CH3 इन एल्काइल ग्रुप मोमेंट 0, एराइल में 0.45. A negative value of group moment means that the group is more electronegative and a positive value means that the group is less electronegative than the alkyl or aryl radical benzene ring. Electrical polarization of molecules. Every molecule is made up of positively charged nuclei and negatively charged electron cloud as shown in the figure 5.9a. The center of positive charges coincides with the center of negative charge. Hence, when such a molecule is introduced between the two plates of an electric field, the positively charged nuclei and hence The center of positive charge is attracted towards the negative plate, whereas the negatively charged electron cloud is attracted towards the positive plate of the electric field. As a result, the molecule gets distorted as shown in the figure 5.92. This is called polarization of molecule, and the distorted molecule with positive and negative end is called an electric dipole or dielectric. The molecule remains polarized so long as the electric field is applied, but goes back to original state as soon as the electric field is switched off. That is why this type of polarization is called induced polarization, and the electric dipole formed is called induced dipole. Since even after polarization the molecule is neutral as well whole, this means that the positive charge on one end must be equal to negative charge on other. Suppose this charge is q. If t is the distance of separation between charges, then dipole moment of induced dipole, called the induced dipole moment represented by mu, will be given as mu L is equal to q into d. Evidently, the value of mu L will depend upon the nature of molecule and the strength of electric field. Say x, we write mu I is equal to alpha into x, where alpha is constant and is called the polarizability of given molecule. Alpha is further found to be related to dielectric constant d of the medium present between the plates, that is the molecule being studied according to the equation put forward by Clausius and Mosity. D minus 1 upon d plus 2 bracket close m by p rho is equal to 4 by 3 pi n alpha, where m is molecular mass of molecule, rho is the density of the molecule, n is Avogadro number. Clausius-Mosity equation. Suppose an electrostatic field is applied to two plates so that they are charged. Suppose the strength of uniform electric field produced between them E naught. Now, if a non-polar medium is placed between the plates, the strength of electric field will be reduced to E, because the induced dipole act in opposition to the applied field and hence partially neutralize the charges of plates. The ratio E naught by E is called dielectric constant D of the medium. From electrostatic, it can be shown E naught is equal to E plus 4 pi I, where I is induced dipole moment per unit volume. I is equal to mu L into N, where mu L is the induced dipole moment in a single molecule and N is the number of molecule per cc. Dividing both sides of equation 4 by E and putting E naught by E is equal to D, we get D is equal to 1 plus 4 pi I upon E, or D minus 1 E is equal to 4 pi I. The intensity of the electric field strength X acting on the each molecule is calculated by supposing that a unit charge is enclosed in a small spherical cavity which is large as compared with the size of molecule but small in comparison with distance between the plates. The electric intensity X is then made up of the following part: the field strength of charges on plates E naught, the charge is induced on surface of dielectric constant with the plates, is minus 4 pi I, the charge induced on the surface of spherical cavity, plus 4 upon 3 pi I. This is our Clausius-Mosity equation derivation. As you can see, as all quantities on right hand side of equation 12 are constant, alpha being constant for a given substance independent of temperature, therefore the quantity on the left hand side of equation 12 must also be constant independent of temperature and depending only upon the nature of molecule. This quantity is called molar polarization and is represented by P. Further, as the applied field produced as induced charge in the molecule by relative displacement or distortion of electron and nuclei, P is often called induced or distortion polarization and is represented by P1 or PD. Effect of temperature on polarization. Using equation 13, the value of molar polarization have been determined for a number of substances. It is found that whereas molar polarization of number of substances such as O2, CO2, N2 and CH4 are constant and independent of temperature, the polarization value for some other substances such as HCl, CH3Cl, CHCl3, C6H CH5NO2 and CH3Cl do not come out to be constant but decreases with increase of temperature. This observation has been the basis of the measurement of dipole moment and the study of molecular structure as explained below. In the case of molecules such as HCl, CHCl3, their center of positive and negative charges do not coincide with each other, thus they possess some dipole moment even in the absence of electric field. The dipole moment thus possessed by molecule is called permanent dipole moment in the absence of electric field. These permanent dipole are oriented in a random manner due to thermal agitations as shown in figure 5.11. However, in the presence of an electric field, the disturbing effect take place. These are the electric field will tend to rotate and orient these dipole in the direction of field. The electric field will tend to polarize the molecule. If the molecule were stationary, the dipole would have been oriented perfectly parallel to electric field, that is at right angle to the plates of electric field. However, due to thermal agitation, they take a position in between that of the original state and the perfectly parallel state as shown in figure B, as shown at B in figure 5.12 for any one permanent dipole. Thus, in case of molecules possessing permanent dipole, the right hand side of equation 13 will give the total polarization, which will be the sum of induced polar polarization and the orientation molar polarization. Measurement of dipole moment, vapor temperature method. The above equation can be written in the form Pt is equal to A plus B by B upon T, where A is equal to 4 upon 3 pi n alpha and B is equal to 4 pi n mu square upon 9k are constant for the given substance. This equation is primarily applicable to gases and vapors. The straight line plots for a few substances with and without permanent dipoles. It may be seen that whereas Pt varies with temperature for HCl, CH3, Cl, it is possessing permanent dipole. There is no effect of temperature on substances like CH4, CCl4, etc., which do not have permanent dipole and hence possesses only induced molar polarization. Method of measurement of dipole moment as explained above. The basic equation for the determination of dipole moment is Pt is equal to d minus 1 upon d plus 2 m by rho is equal to A plus B by T, where A and B are constant with B is equal to 4 pi n mu square upon 9k. Thus, the experiment involved the determination of dielectric constant D and the density rho at different temperature T. The values of Pt are then calculated and plotted against 1 upon T. If Pt is found to vary linearly with 1 upon T, the substance possesses a permanent dipole moment and the value of dipole moment is calculated from the slope of line. On the other hand, if Pt is found to be independent of temperature, the substance does not possess any permanent dipole moment. The dielectric constant required in the above equation is determined by first measuring the capacity of a condenser in vacuum between the plates C0 and thus measuring the capacity of same condenser when filled with the given substance C. The dielectric constant of given substance is given by D is equal to C by C0. Now we will discuss about magnetic susceptibility. General introduction to some terms used. Magnetic permeability. Two magnetic pole of strength m1 and m2 are separated by a distance r, then the force F acting between them is given by F is equal to 1 by mu1 m1 into m2 upon r square. The quantity mu used in above expression is called magnetic permeability of medium between the poles. It is defined as the relative tendency of magnetic lines of force to pass through the medium as compared to that in the vacuum. For vacuum, mu is taken as equal to 1. Similarly, for air, mu is taken as approximately equal to 1. Diamagnetic and paramagnetic and ferromagnetic substance as mentioned above. The for vacuum, mu is equal to 1. For other medium, mu can be less than or greater than 1. If mu is less than 1, then the magnetic lines of force prefer to pass through the vacuum rather than through the substance comprising the medium. In other words, the magnetic line of force are repelled away from the substances. Substances are said said to be diamagnetic. On the other hand, if mu is greater than 1, then the magnetic line of force have been greater tendency to pass through the substance rather through the vacuum. In other words, the magnetic lines of forces are attracted towards the substance. Such substances are called paramagnetic. If mu is very high, the tendency of substance to attract the magnetic line of force is very high and the substance is said to be ferromagnetic. Ferromagnetism is exhibited mainly by iron, cobalt, nickel and their alloys. It is a property of greater interest in the subject of physics. Only in chemistry we will deal only with the diamagnetic and paramagnetism. The behavior of diamagnetic and paramagnetic substances in magnetic field is shown diagrammatically in figure 5.19. Magnetic susceptibility as shown above. If any material is placed in a magnetic field, the strength of the magnetic field in the material is different from that in the vacuum. The strength of magnetic field thus present in the material is called magnetic induction. If H is the strength of the applied magnetic field and B is the magnetic induction in the given material, the two are related according to the equation B is equal to H plus 4 pi L, where I represent the magnetic moment per unit volume in the material and is called intensity of magnetization. It may be positive or negative depending upon the whether the material is paramagnetic or diamagnetic. The intensity of magnetization produced per unit strength of applied magnetic field is called specific magnetic susceptibility. It is usually represented by X. This mathematically X is equal to 1 by H. It is this quantity which is usually measured experimentally in the study of magnetic properties of multiplying measurement of magnetic susceptibility. The magnetic susceptibilities are generally determined by the method put forward by Gould in 1889. The material under examination is taken in a thin cylinder on a tube which is then suspended vertically with a wire from one arm of the balance between the two poles of an electromagnet such that the lower end of cylinder is nearly in the middle of the pole of the electromagnet. The cylinder is now counterbalanced in the position by placing weights in other pan of balance. The current is now switched on into the electromagnet. If the substance is paramagnetic, the cylinder will be pulled down so that more magnetic lines of force can pass through it. On the other hand, if substance is diamagnetic, the cylinder will be pushed upward so that the less magnetic lines of force may pass through it. In the first case, some extra weights will have to be added into the, whereas in second case the some weights which have to be removed from the pen to restore the balance, since the change in weight is equal to magnetic force acting on the material. Hence, if delta m is the change in mass, then we have delta mg is equal to 1 half x minus x ah square, where g is the acceleration due to gravity. So delta mg gives the change in weight. The right hand side, the magnetic force acting on material of volume susceptibility x, when a is the area of cross section the specimen, h is the field strength and x is the volume susceptibility of the air. Explanation of diamagnetism and paramagnetism. Electrons in an atom have orbital motion as well as spin motion as they are charged particles. Therefore, their motion produces a small magnetic field. If all the electrons in a molecule are paired, the magnetic moment of electron spinning in one direction is cancelled by the magnetic moment of the electron spinning in opposite direction. The net result is that the substance has zero magnetic moment. If such a substance is placed in a magnetic field, the small magnetic moment is induced in the substance in opposition to the external magnetic field. As a result, the substance is repelled by the magnetic field. This type of behavior is observed for the diamagnetic substances. Thus, diamagnetism is exhibited by those substances which contain paired electron only, that is, no unpaired electron is present. On the other hand, if a substance contains some unpaired electrons, the magnetic moments of electron do not cancel out completely. Hence, the substance has a permanent magnetic moment of its own. In fact, each unpaired electron behaves like a micromagnet with a definite magnetic moment. If such a substance is placed in an external magnetic field, the micromagnets will arrange themselves parallel to external field and the induced magnetic moment is is insufficient to overcome the permanent magnetic moment of substance. Such substances are therefore attracted by the magnetic field instead of being repelled. Is observed for paramagnetism. Thus, paramagnetism is exhibited by those substances which contain some unpaired determination of magnetic moment of a paramagnetic substance. As explained above, each atom, ion, or molecule of a paramagnetic substance behave like a micromagnet with a definite inherent magnetic moment of magnitude μm. When such a substance is placed in the external magnetic field, the micromagnets tend to arrange themselves parallel to the applied field. However, this tendency is opposed by the thermal motion of the particles, because magnetic susceptibility of micromagnetic substance varies with temperature. Hence, the actual arrangement taken up will depend upon the temperature. Relationship between magnetic moment and the number of unpaired electrons. The total moment of any atom, ion, or molecule is the sum of the following two values. Magnetic moment due to orbital motion of the electron, it is equal to under root of L plus 1 Vm, where L is the azimuthal orbital quantum number for that electron. Magnetic moment due to spin motion of electron, it is equal to 2 S bracket S plus 1 bracket close under root Vm, where S is the spin quantum number having value equal to half. If ions or molecules are considered instead of free atoms, it is expected that orbital motion of the electrons are tied into nuclear configuration of molecule or the ion so tightly that they are unable to line up with the applied magnetic field. Dielectric properties of solids. Insulators do not conduct electrically because the electrons present in them are held tightly to the individual atoms or ions and are not free to move. Such polar crystals show the following interesting electrical properties. Piezoelectricity or pressure electricity. When mechanical stress is applied on such crystals so as to deform them electrically, is produced due to displacement of ion. Pyroelectricity. Some piezoelectric crystal, when heated, produce a small electric current. The electricity thus produced is called pyroelectricity. Py means heat. Ferroelectricity. In some of piezoelectric crystal, the dipole are permanently polarized even in the absence of electric field. Antiferroelectricity. In some crystal, the dipole align themselves in such a way that alternately they point up and down, so that the crystal does not possess any net dipole moment. Such crystals are said to antiferroelectric. A typical example of such crystal is lead zirconate, PbZrO3. Uses of above properties of solid. The various properties of solid as explained above are being used in electronic and magnetic devices such as transistors, computers, and telephones. Thank you.